discussed quite a bit of this before, I think, last time. So we'll have a look at solutions on it, and then we'll move to question 3. Start with question 3, okay? So the first part was just to give 2 definitions which are relevant for some of the rest. Generator of a group and that of a cyclic group. So Jan says for a group element, he's defining the notation for, well, it turns out to be the cyclic subgroup generated by this element, but just as a set, it's this set of elements. A set of all integer powers of the element G. This is certainly a subset of G. This is some group elements. And it says G is a generator if this set happens to be the whole of G. And, kind of flip side of the coin, or associated to it, G is a cyclic group if it has a generator. That is, there exists an element, little g, which has this property. How many marks? How many marks should we give it? How many did it work? Well, it's 4 in total, so I'm assuming it's 2 and 2. 4. Yeah, I mean, we'd be pretty picky to refuse those marks. So I can't really see any grounds on which you could. I mean, while you're at it, why not name this as cyclic subgroup generator? That's fine.
What are you going to ask? What is the definition?
Well,
subgroup generator.
Yeah. When you write these questions, though, sometimes you don't know what you're asking for.
It's very getting to this question because
So B, the generators of the cyclic group Zn of order n are the integers R. Okay, between 1 and n, fair enough. They're what we speak of as the standard representatives of the congruence classes. But you must have GCD of R and n to be 1. So it's only when they're co-prime are you looking at a generator. This is a result from the book, which is presented in multiplicative notation. Okay, so it's all about powers of elements. Whereas here, we use additive notation for Zn. So you present the argument in terms of multiples of an element, perhaps. So very good. So Jan is telling us about the structure of the proof. Okay. First of all, he just, for his own benefit, the benefit of the reader, just remind ourselves what Z is. It's a cyclic group of order n with these elements 0 through n minus 1, but addition modulo n. And so he splits the proof up into 2 arguments. He's going to show that if something has a non-trivial greatest common divisor with n, that it fails to be a generator. Secondly, if it has GCD 1 with n, if they're co-prime, then the order of R has, okay, then he's going into the proof of it, but yeah, probably to mirror that, you maybe should have had the title of what you were going to prove. So he's going to prove if it's co-prime, then it is a generator of n, or it has order n. R has order n, and therefore it must generate the whole group. Yeah. So that's good to split up your argument like this. It's easier to present. And so this is how the proof goes. So if the GCD is D, which is non-trivial, then it's basically, we notice that we can, we want a power of R, except in additive notation it's going to be a multiple of R. We want a multiple of R to be divisible by n, but when we're using the coefficient of the multiple, like the exponent before, but now it's a coefficient and a multiple, we want it to be less than n. And that's going to show it will have order less than n. Okay? Because you're equal to the identity when you're congruent to 0 modulo n, when you're divisible by n. being congruent to 0 mod n means being divisible by n. So he looks at this multiple of r, n over d times r, and you can finesse the denominator d and put it over underneath the r instead. And d is a common divisor. D is a divisor of r. So this is an integer multiple of n. So we can say that n divides it. Okay. Otherwise known as k. K times r. K is strictly smaller than n because d is not 1. So the order, now yeah, we haven't proved that the order is k, but we proved that the order has to divide k. Has to divide k, so it's certainly less than or equal to k, and this is strictly less than n. So order is not to generate, okay, because it has its order is too small to be generated. Okay. So it's an important characterization to be aware of about order, which you use elsewhere. Not only is order the smallest power of the element before you get back to the identity, if there's any power of the element that brings you to the identity, it's a multiple of the order. Okay? So the order has to divide it.
But we don't need it.
No, we don't need that divisibility here. So secondly, he's saying if it's co-prime, then does have order n.
So what we're actually using, sorry,
Yeah.
you don't mean that it divides it, but if you have a power which is the identity, then the order cannot be larger than that.
Yeah.
Because the order is the smallest such k.
Yeah. So yeah. So not relying on the divisibility fact, but just the fact that order is defined as the minimum such thing. So you see one of them, the order has to be less. And so the order of R, which is sigma.
No, it's an O, you wrote it.
It's an O.
Yeah.
Well, you wrote it. I didn't say.
Well, you wrote it on the blackboard.
Oh yeah, you copied me. Yeah, O is a problematic symbol to use. It looks too much like 0. That's why it's got the little script twiddle on it. Anyway. So the order is O. It's the minimum multiple of R, such that n will divide it. It has to satisfy n. Yeah, so by definition, n divides the order of R times R. But here's where we're using this special property that the GCD is 1. So when this divisor n is co-prime to R, the only way it can divide the product is if it divides the other factor. Maybe put in a justification, this is because they're co-prime. This is true. This is the kind of thing that you can, because they're co-prime. So if n divides the order, you then claim so the order is equal to n. Probably you need the observation or need to make the point, kind of say, of course, n divides n times r. So the order is less than n, and here n is less than the order is less than or equal to n, and here n is less than or equal to the order. Therefore, the order is equal to n. Because here you would say n is less than or equal to the order.
Yeah.
And then, trivially, of course, n does divide n times r. So n is one of the elements in the set, so the order is less than or equal to n. And then with those two, you can then claim that the order equals n. So if it's got order n, then it generates a subset of size n inside here, but then it has to be all of it. Mind if I augment?
Augment.
Huh?
So you
Just
just
say-
say.
clearly n divides nr. So the order is less than or equal to n. Divides n, but it's less or equal to n. And here he has the other way around, n less or equal to the order, so you can conclude that there. Okay. Any related questions or points about it? Queries?
So why if n is less than r, then the order is less than n?
Well, because he's defined the order is the smallest number, smallest positive number, the smallest number in this set, which is the set of all multiples mr, which make this product divisible by n. And clearly, this n here qualifies as one of those n's. So this n here qualifies as one of the elements of this set. So the minimum of the set has to be less than or equal to it. Yeah? Also be looking for, when you're proving things, if you can't separate the argument into cases or the two directions for an if and only if, etc. That kind of thing can be helpful. Sometimes if you can't see how to do it, or you're failing to express the proof, maybe you're trying to do too much with a single argument, and it needs to be split into cases or something. Okay. So that was the 6th marker. That was perhaps the hardest part of this question, I think.
Maybe it is.
Huh?
Yeah, it's a textbook.
It's a textbook argument.
If you happen to know groups in the
Okay, can I turn over? Can I turn over, Georgia? Yeah. Okay, so part C. Is every cyclic group abelian? Prove or disprove? So the answer here is yes, it is. Any cyclic group can be presented in this form, the set of powers of its generator. So you can treat any element in capital G, it's just some power of this one fixed element of G. And so multiplying elements of capital G then becomes multiplying powers of G, and all your rules of indices hold. In particular, these are just integers. So when you multiply two elements, so two typical elements is one power of G and another power of G, K1 and K2. So if you want to multiply them, you're multiplying powers of G, you're raising G to the sum of the two exponents. And that is abelian, because addition of integers is abelian, so that can be reversed the other way around. Yeah, strictly speaking, you want to put in an intermediate. This equals G to the power of K2 plus K1. But
I'm assuming they're going to marking everything.
Yeah.
Fundamental intelligence.
well, yeah. But the guy marking it wants to know that you have to be. The person marking it wants to know that the person writing it has to be. Okay. So you could say the cyclic group gets its abelian nature from the abelian nature of adding exponents. Okay. Part C is the symmetric group cyclic. Now Jan has done it by explicitly investigating. He's listed all 6 elements of S3. He's interrogated each one to find out its order and shown that none of them are order 6. Okay? But someone suggested an alternative method last week, which was we could use part C either. We can either demonstrate that, sorry, we have to show, is the symmetric group S3 cyclic? Well, we can show it's not cyclic by showing it's not abelian. So if we show it's not abelian, then it couldn't be cyclic, because if it's cyclic, it has to be abelian. So, perhaps that's more straightforward, or it probably makes for a shorter proof. Just give a product that doesn't commute. So any product of any two cycles, or a 2 cycle with a 1 cycle will not, or a 2 cycle with a 3 cycle will not commute. So you can just show that. Just write down those 2 products there. They don't commute, so the group isn't abelian, therefore it's not cyclic.
Why did you say that they are not generators, those guys?
Well, because, so he explicitly investigates the subset generated by the element and lists the elements in the subset and is just observing. So this is 3. So this is has order 3. 3 cycle has order 3. 2 cycles all of order 2. So none of them give you all of the elements. Yeah. So there are no generators. So it's not. Okay. So an alternative, quicker approach to D is to show that it's not abelian. Okay. So now continuing asking about permutations, they prove that the product of two even permutations is even. Well, we haven't seen the definition in the question, before that. So really, you should start this question with putting down what the definition of even is, yeah? Just to fully assure the marker that you know it, and also to get it front and center in front of your own eyes, so that you can then build the argument on it. Yeah. So just quoting the definition, a permutation is even if it can be written as the product of an even number of transpositions. Cycles of like 2. So you can give a direct proof of this. If sigma and sigma prime are even, then you can express sigma and sigma prime as a product of transpositions tau I, and tau I prime. And importantly, they go up to, and there's an even number of them. I've got a prime on his K as well. So he's not claiming that there's exactly the same number. This one could be very, very long. This one could be very, very short, but that there's an even number of both. Okay. You don't have to do it with primes, but yeah. Different letters. And so then, okay, so the principle he's using here, that if you want to then compose these two, well, you just, it's a nice word, concatenate the 2 products, okay? So you do sigma prime first, which is this, and then follow it with sigma, which is products of these transpositions. And how many transpositions do you have there? 2 times k plus k prime, which is clearly an even number. Okay. So the product is even.
So is that O prime? O dash?
Sigma dash.
And that is sigma
Yeah,
dash.
yeah, the same as well. Yeah, it's a little indistinguishable. Why don't you was?
3 marks.
Oh yeah, 3 marks.
Oh, yeah.
Is there anything deficient? I don't know. I don't think so.
Sigma's going to look like Sigma's.
Yeah. F. So what's F saying? This is what, later on we understood this is an example of a way to construct a group action of a group on itself. But anyway, what it's presented as here is you take a group you consider a fixed element little g, and then you can associate to that fixed element little g a map from the group to itself, which is left multiplication by g. Okay, so it's a function, give it any argument a, the value you get is g times a. Prove that this is a permutation of g. So he's just got a reminder here to himself of the key definition from the question. And yeah, again, just like the question on even permutations, it's good to start your thing with a quote of the relevant definition. Okay, so this is a kind of general view of a permutation. A permutation of a set is an injective and surjective function from the set to itself. Okay, so a permutation of a group, well, a group is a set, so it's just a bijective function from the group to itself. So you got to prove injectivity and surjectivity. The standard way to prove injectivity: assume you've got two arguments which give the same value. Prove that the arguments must be, in fact, be the same element. So these are the values, GA and GB, and by the cancellation property, that implies A plus B. Or you could phrase it as multiply both sides by G inverse on the left. That is the cancellation property. You get A plus B. Yeah, so surjectivity, you take a typical element from G, and what you want to show is that this occurs as a value of the function. So you want to show that lambda times something, so this is a bit mysterious at the beginning, lambda times something equals B. And whatever that something is, you're going to multiply it by G on the left. So what group element do you multiply on the left by G to finish up with B? Well, it has to be the group element, otherwise known as G inverse times B. Okay, because you want to get rid of the G, which comes from the definition of lambda, and you want to end up with B. So you use G inverse to get rid of G, and then you have B to keep B. Okay. So G inverse B is the correct thing that fills the space to give you B occurring as a value of the function. Therefore, it's surjective. And that will work for any B at all, so therefore it's surjective.
So you say A belongs to then G inverse B belongs to.
Yeah, so why is that true? Did you need more justification for that there, or should I just accept the candidate saying that?
I just don't know where to get that. What's the first one? B belongs to G. Where do you get G minus 1 from?
Well, it's in the group.
Well, G is the fixed element that comes with the lambda.
Yeah. So the fixed element is provided for you, little g's, stated in the question.
Okay, and inverse in that is also in that group.
Yeah, because it's a group.
Yeah, okay.
So a group has inverses for every element in it.
Yeah.
And so the inverse is in G, so this is just an instance of the closure property. Combined instance of the inverse property and the closure property. Again, this is a further on kind of higher level question, or further on question. Yeah, we wouldn't be looking necessarily for constant reference back to the group axioms, when you're up to talking about this stuff, Fair enough? Yeah? Any related questions that spring to mind from those topics? Okay, good. So the next question we should devote attention to is question 3. Some people have started on already. Which parts A and B is pretty much a guided, a skeleton proof of Lagrange's theorem. I quite like that big question on the coursework. Stepped you through all these subparts to get a result. This is stepping through these intermediate results and guidance to build a proof of Lagrange's theorem, which you're asked to state in part A. And then part C, now this did come up with this. Part C, I think, is an exercise from the book. It's when you got two subgroups, you can have, it's called a group. double coset of H and K. I think. Is that right? Double coset. Maybe double coset. I'm not sure. It's a double coset multiplying one subgroup on both sides by now. I'm not quite sure. But you're showing here that if you got any two subgroups H and K, you can define a relation by saying two elements G1 should be regarded as equivalent to G2, no, should be regarded as related to G2 if you can find elements H and K. So this is kind of like a conjugation, except not exactly. So an element H from H, an element K from K, such that HG1K gives you G2. It turns out this is an equivalence relation, so you're asked for the definition of an equivalence relation and a proof that this relation is an equivalence. So do have a dive in there into your notes or in discussion with others to see how you would answer this. Got any queries you want to ask? If you do, and talk. And then tomorrow, Jan is away tomorrow, so I'll be here for a week. I'll go through my solution question 3. Or you can give me a solution. Free rank to terror class. You working on question 3?
Yeah.
Yeah, that's going.
It's all right. Yeah, we don't know.
With the all cosets of H contain the same number of elements.
So what you say?
How many they all contain?
How many do they all contain?
The size of
Ah, so how can you use that? How can you leverage that?
That's the problem.
Very general principles. How do you show that one set has the same number of elements as a reference set?
Is that one?
Yes.
Yeah.
What kind of mapping?
Object.
Bijection, yeah.
Because like I know that, but I have to.
Can't put it down.
So try and construct one.
Well, so far, you've shown that it was. You take the identical. That's the way.
So you can take that as a fact about finite sets, and for infinite sets, it's the definition of when they're regarded as having the same number of elements. Existence of the bijection.
It's just really annoying, but you can't do that.
Right?
Can't do part 4 without part 3.
Oh, my question is that
Yeah, to show it without proof.
you know when you say since G1K equals G2, what do you mean of the 31K G1K?
This one here.
Yeah.
So this is what he's doing here. You're given two subgroups H and K. This is giving the definition for a relation. So for a binary relation, right? So a binary relation is a rule for constructing a statement. An operation is a rule for constructing another element, say, from a product of two elements. A relation is a rule for constructing a statement, a sentence, which is either going to be true or false, depending on the inputs in G1 and G2. So the statement is, you can find elements little h and little k that will give you this equation between G1 and G2. So for particular G1 and G2, that might be true or false. If you can find, if these little h and little k exist, then we say G1 is related to G2. If they don't exist, we say G1 is not related to G2. Okay. So it's a rule for constructing a statement. And it's a rule for when you do and do not link together elements and regard them as being related in this ordered sense. G1 is related to G2. It turns out it's the nice kind of relation, what we call an equivalence relation, one that acts like equality.
It's not exactly equality, it's the kind of relation that groups things together in equivalence classes. Then in the equivalence class, everything is related to everything else. But different equivalence classes, nothing is related to anything else in the other equivalence classes. Not every relation splits the domain up like that. Only equivalence relations split the domain up. Disjoint sets that partition the domain.
So this is assessing whether you know the precise definition of an equivalence relation. There's three, can you remember the three properties? Three properties. Have you been working on it, Amy, yet? Reflexivity, transitivity, and symmetry.
That's all I said for you that night.
And you probably want to get the predicate statements of each of them. Yeah.
I hate how you write it.
Right,
Like, is it all right?
Oh,
Like,
yes.
instead of this.
Yeah, I have seen
They write, yeah, so some people write that, so
Yeah.
they declare a set of ordered pairs. Okay? So for them, a relation is a set of ordered pairs. This is related to that. That's kind of in a similar way in that you can define a function. What is a function? One way of presenting or constructing it is a function is a set of ordered pairs from argument to value. They're the ordered pairs, it's just the set of all of those ordered pairs. So that's the kind of way, when people say everything is sets in mathematics, that's kind of what they're talking about.
Yeah.
Those are things they're talking about. Everything can be rendered into sets.
You know, if you can't prove it, then it'd be very much, you know, actually reason to find why. You can't do it, it's very annoying. I can't rate it.
Try talking through it. Trying to work it out. Just proving we have the same number of elements.
I mean, you phrase it a bit.
Well, I'm tempted to just say they're all just this, so it's just definition.
Well, you talked about maps before, so have you?
I've got as far as writing that down.
You have to say that there's a bijection.
Yeah. Yeah.
So at least clearly articulate what the function is, what the mapping is.
That would be a problem.
Yeah.
So,
Oh, so there is some element. It's probably the inverse. Just to get G1 H to go to G2.
now you're making a little bit,
Complicated.
yeah. Then because originally you told me you know how many elements they all have. It's
They work the same thing.
whatever the size of H is. So you use H as your reference. Rather than showing everything in the set has the same number of elements as something else. Yeah, just show everything has the same number of elements as G, the set, as H, subgroup H. If everything has the same number of.
What are you giving them hints? I think that's what it is.
Oh, yeah, but you're.
I'm sure it's in the book. It's in the book.
It is yeah.
Still.
You haven't paid a tuition fee, so.
Oh, it's in the book.
Yeah, there's one where it proves when the word
Good
black
one.
is the same.
Oh,
Yeah. I assume it's relevant specialist.
So you can't but it's just you're making life a little bit too difficult for yourself. You show that this general thing has the same number of elements as that general thing. Instead, show every general thing, every left coset, has the same number of elements of
Oh,
the
wait, no, I found it.
subgroup H.
yeah, it's in the book.
So you needed to have an inverse because I stopped when it's well, until it's getting further. I hate myself. It's the first bit.
Okay.
Yeah, sure. Did you say non philosophy?
Ah,
Non philosophy.
no.
Okay, why does it say that the left forces are in for either
That's
equal
the
are either equal or disjoint?
Yeah, so this was one of the key steps in the way we presented the Ronch's theorem.
So,
Okay. So this is true of left cosets. So it's asking you to prove it. So you can never have different cosets partially overlapping. Different cosets are disjoint. They don't share any elements. Okay. So if you're presented with two representatives, G1 and G2, they will each generate their own left coset. The options are only they're exactly the same or they're disjoint. You can't have that G1H partially overlaps the G2H. They're completely disjoint or they're exactly the same as sets, as subsets in G. It's that fact that means that the left cosets partition G. Split G up into equals, well, into subsets, and then in here you're proving each subset's the same.
Yeah, I was like, now what? I was like, no, that's shown it.
Yeah.
We did show it.
Yeah. Well, using equations like that.
So just get to an answer and then I'm like, shit, now what? And I'm like, no, that's the answer. You did it already.
Is it enough to just say by a lemma in the book?
That depends on what you're being asked to
So
do.
like here, I've got to that stage and then I've just said by a lemma in the book.
G1
Do I have
is
to
an
show
element of
this?
G2H, so none of the books.
Just say in the question, lemma is proves.
Yeah, so something, well, I mean,
It's just
that
it's-
is, you kind of accept what is
Because
said everywhere, if you're going to use something stated here. Yeah. So, so this is for proving that they are not going to be disjoint. So if they intersect at all, then the generator is an element of the other one. Yeah, I think that would be acceptable. Yeah, because we did have the lemma that gave multiple criteria.
And so
They're all equivalent. Yeah, that's fair enough. I mean, you can kind of see why. So, like any element of G1H is going to be G1 multiplied by something. Equally well, by substitution, you can regard that as G2 multiplied by, well, you've got your something from H, which you put on the right, but then it's just multiplied by two other elements. So that again is something from H. So anything in here is contained in here, and vice versa. And we'll put these H's over here to the right of G1 by inverting them. And then G2 times anything from H will be just another instance of G1 times something from H.
But here it's saying G1H equal to G2H, but how is
Well, not equal to, should be an element of, because she's written G1 as G2 times something which is clearly an element of H.
okay, so it's G1 that is equal to LOH. And then how do you end up in G1H equal to G2H?
Well, she's referencing a result of the book.
What's that result?
Namely that this statement and that statement are equivalent, or that one applies on. I mean, the thing the book said they're equivalent. So she's making use of the fact that this, it's enough to show this.
Everyone was at some time. It's a lot, right? More than.
4 and maybe 4 and 5.
Still got, you've got at least 40 minutes.
Yeah.
One question, so, you know,
I feel like an hour, but I was not with
yeah, so you're into exam mode. Yeah. No, done.
Yeah.
What are you talking
No, I'm doing on chest first.
It's because you called me down.
I'm just gonna go down, can you?
Oh, Dave.
Don't call me down.
That's what you get for leaving class early.
them.
You called the wrong name.
So that is my fault.
Well, that was that.
I was about to say that was my father. Not so
I think you'll be hearing that a lot if you go down your chest.
Oh, yeah.
Mr. Shuttleworth, sir.
Can I
Mr. Shuttleworth.
not be that, can I not be that cool teacher? Call me Danny, look around with you kids, sit backwards on a chair.
No, because you will.
Oh, yeah. I'll do Mr. Short. Then what?
I think it's well better than like men get called sir, but then women just get called miss, which is like pretty common.
What would you
Sir
rather?
sounds
Yeah,
Because-
because everybody
My dad.
get by.
Yeah.
It's
Yeah.
like,
When I went to Bolton School over the summer to get some experience, they call all the private school, they call all the teachers.
Oh, really?
Yeah, so it's.
why do you yell sir?
Uh,
Like, who missed it?
Because
missed it.
They'll
I
stop
don't
it
know.
till it takes
You
one.
missed it.
Yeah, we did that.
We threw chairs.
I don't miss it.
After we got to the nice school.
No, they didn't want to be called just sir. You just
By year
combined.
10, I was calling my teachers by their first names. Like, my entire year was just calling by their first name.
In college, that was the policy. There was only one physics teacher who was really old who refused to give solid
Yeah, I
space.
thought it was normal in college, but then
No,
I talked to
I-
people and everybody was like, oh, we start to call them this.
I went to the sixth form in my school, so it was all the same teachers we had.
Yeah, they just switched your
They
first
just-
names back.
None of them would let us just name. Like, we still did, but we were like, no, we want to do this. No, still no, yeah, right.
I was in the middle of answering questions.
Deal with justices.
So that-
The doctor.
One thing we have.
Oh.
Is that on the video? I'm sure no one knew.
Is it recorded?
Is it in here that always calls overtures?
Oh,
What's his
cash.
name?
Catch, yeah.
He would fire me.
Every time. So, where are